Hi, my name is Ghous, and today I'll be presenting on our work titled Dynamic Volume Hiding Encrypted Multimaps with Applications to Searchable Encryption. This is a joint work done with Server Patel, Giuseppe Persiano, Kevin Yu, and Moti Young. This talk will be broken into the following main parts. I'll go over what background is required for encrypted multimaps. Then I'll talk about what volume hiding means. Then I'll discuss our constructions and finally finish with some key takeaways. So let's start. In today's world, a lot of data is stored in databases on the cloud. This data includes our sensitive health records, our private information like communications and financial information, etc. Unfortunately for us, even if we trust the server, which would be a no, these databases are very unprotected from external adversaries that can break the server and steal it. Now, there are roughly two ways how this data can be stolen. One is the adversary compromises the application and queries the data. Second is the adversary breaks into a database server. We are more concerned with this option because here the adversary gets to see the transcripts of all the queries and the updates as well as the data. This adversary can be the server itself. Now, one way to defend against such an adversary is to keep the data encrypted on the server. But the issue with that is that you will lose on this functionality the server might provide, like search. So the question becomes, can we essentially encrypt the data on the server and still query it? And the answer is yes, we can for quite some time. But there's a trade-off to keep in mind between efficiency, functionality, and privacy leakage. For example, if you want an efficient scheme with more functionality, you might have to lose on privacy and leak more to the server, and so on. One building block to achieve an encrypted database is a structured encryption scheme, which is a nice balance between efficiency, functionality, and leakage. Client has a data structure, some sensitive data in it, which it uses a setup algorithm to create an encrypted data structure that it sends to the server. During the execution of the setup protocol, the server might learn the size of the data and some other information, which is captured by the setup leakage function, or LS. In a similar way, client has a token algorithm for querying. A client generates this token for a query and sends it to the server. The purpose of the token is to hide the plain text query from the server. The server uses this token, applies it to the encrypted data structure, and produces a response that it sends back to the client. What is learned during the query protocol as well as the token protocol by the server is captured by the query leakage. This could be whether the search is repeated or what is the size of the result set. Similarly, I'm not showing the lines on the screen, but client has an update token algorithm which produces an update token. It sends a token to the server. The server applies this token to the encrypted data structure to produce an updated encrypted data structure. What it learns during this execution is captured by the update leakage function, or LU, by the server, and so on. So this is what structured encryption was, but what the data structure we'll use in our talk would be the multi-map data structure. So are they? Multi-map map labels to tuples. For example, L1 is mapped to V1, V3, V4 here. And if I try to get L3, I'll get V2 and V4. So, but why do we care about them? Because we care because they are a very powerful search primitive called inverted index. An inverted index is basically a multi-map that looks like this. It maps keywords to document identifiers, which means that if W1 is mapped to ID1, ID3, and ID4, which means that the keyword W1 belongs in the documents identified by ID1, ID3, and ID4. Now, on the screen, you can see that we have instantiated our data structure with multi-map and encrypted data structure with encrypted multi-map. Next, we'll talk about the security of a structured encryption scheme. In order to prove that an STE scheme is secure, we use the following security notion. It guarantees that the setup algorithm and encrypted structure reveals no information about the underlying structure beyond setup leakage. Query algorithm reveals no information about the structure and the queries beyond query leakage. Update algorithm reveals no information about the structure and the update beyond the update leakage. If this holds for adaptively chosen operations, then the scheme is said to be adaptively secure. Now that we're all caught up on structured encryption and encrypted multi-maps, let's discuss dynamic volume hiding. As the name implies, the goal of volume hiding is to hide the volume of keywords in the encrypted multi-map. For example, look at this multi-map. W1 is mapped to a tuple of size 3, W2 a tuple of size 1. The goal is to hide these sizes during setup, query, as well as an update protocol. A big motivation to construct volume hiding schemes came because of a attack paper from Blackstone et al. In 2019 that exploited volume leakage. But why is this leakage bad? Because essentially it reveals information. Because take a hospital setting, for example. A doctor might want to decide to store medical information about currently hospitalized patients in an encrypted database. When a patient name is queried, the size of the result might reveal how many tests have the patient undergone, and so on and so forth. This information, coupled with auxiliary information, could help reveal an attacker the name of the patient in plain text, even though everything was encrypted. So uh, now clearly volume height is important, but PyBark has only dealt with static encrypted multimap so far, i.e. they do not support updates. And in case of KM19, only semi-dynamic updates, which means not all type of updates. Also, with full dynamicity comes the requirement of additional properties such as forward and backward privacy, which we will not go over in this talk, but our schemes have them simultaneously with volume hiding. And to that end, we present our first fully dynamic volume hiding scheme. Next, I'll quickly talk about our volume hiding leakage functions, a definition of them. Adversary picks two multimaps MM0 and MM1, with both are bound by maximum size of n and the maximum label volume size of m, and it sends that to the client. The client picks a challenger picks a bit b, and runs a setup algorithm on MMB and sends the setup leakage to the adversary. The adversary then sends a query to the challenger. The challenger applies the query to MMB, and adversary receives the query leakage from it. The adversary can pick two updates, U0 and U1, and send it to the client. The client will apply the correct update to MMB, and then the adversary will receive the update leakage from it. Now, in order to make the game non-trivial and correct, both U0 and U1 updates must be on the same label and have the same operation type. Only the tuple sizes can vary. And this can go on for a polynomial number of turns, and the adversary will try to guess the bit B. And at any point during this function, the challenger can abort the game if the multimap size exceeds n and the label volume exceed m. Now, all our schemes have volume hiding leakage functions that we prove in the paper. Now let's move on to our construction. There are many challenges came up during this process. We needed to keep the dynamic encrypted multimap volume hiding and efficient at the same time, close to static schemes as possible, and all of that by using efficient primitives. And in order to do that, we came up with our scheme 2CH. The gray lines on the screen is our encrypted multimap. The other one is an input multimap. The maximum size is n, the maximum volume is m, and the bin size, so each gray line represents a bin, and the bin size is log n. We use the choose choice hashing by Azar et al. As the building block. Now, what we do essentially is that we pick a label value pair, for example, W1ID4, and we hash it to two bins, and we put it in the less loaded bin. Here, both bins are empty, so we put it in any bin. Then we encrypt it. Same, we take another label value pair, we encrypt it, and we do it the same thing for everything. And hence and that's how we populate the encrypted multimap. Next is that we do have a client stash here, but analysis shows that the client stash doesn't grow more than omega log n with negligible probability. Our experiment, however, show that it only holds a couple of items at a time, which is amazing. At the end, we pad the bins with empty values and encrypt them so that the server will not learn which ones are real and which is fake. And that's how our setup protocol works. Next is the query algorithm. Now imagine you want to search for W1. The client will generate a token for W1 the following way. Remember how each value mapped to two bins. So the first value for W1 will map to two bins. So these are two hash computations to identify the bin. Then the second value will two more bins, third two more bins, fourth, and so on up to m bins, because the maximum label volume can be m. Now the adversary gets all of these bin identifiers essentially, and the adversary returns two m bins. I keep saying adversary. What I mean is the server, which we do not trust. And so it returns two m bins. The client will then decrypt and retrieve the result. In the paper, we have a way to show that how instead of sending two m tokens to the server, we only send one token. Now, for our update can be of the following forms. We can append a new value to a tuple, we can delete a value from the tuple, we can edit a tuple, or we can remove the key value tuple altogether. And in order to do that, we simply do these three steps. We send a query operation for a keyword, which we want to do an update on. We receive the 2m bins, and then the client simply updates those 2m bins after downloading them, and then he re-encrypts and re-uploads them to the server. And you have an update. Now let's talk about leakage. During setup, the only two things that the server learns is the upper bounds, NNM. During query and update, however, it learns key equality, which is whether the same operation was repeated. Whether the operation was repeated on the same keyword, be it a query operation or an update operation. And the cost of mitigating this is logarithmic, identical to using oblivious rams. And we also leak type of operation, which can be mitigated. We show that in the paper, and we have dynamic volume finding leakage function. Again, which we prove it in the paper. Now, in terms of efficiency, our update and query complexity are m log n. Our encrypted multimap size is n log n, but we have an ON variant at no additional cost in the paper. We have more schemes. We have 2CH FP based on 2CH, but this is additionally forward and backward private. Again, I'm not going on into what forward and backward privacy are, as this talk is very short, but these are de facto standard security properties that a lot of current state-of-the-art schemes have. And in order to do that, we use a secondary encrypted multimap only for updates on the server. And because of that, we need to use a count table that most schemes use in literature on the client to help resolve these updates. In order to get rid of this count table, however, we have another scheme, 2CH SFP, that essentially uses multiple encrypted multimaps of geometrically increasing sizes on the server to help resolving updates. Instead of the count table, we just get rid of it. However, we have an additive log n cost at query time due to that, because we first have to query these increasing geometrical sized encrypted multimaps and then two other steps. And details are available in the paper. We have evaluations. We have a lot of graphs in the paper, so you're very welcome to take a look at that. However, some key values. Setup protocol takes up to 36 seconds for 2 to 22 values for almost all of these schemes. Query protocol takes 0.04 millisecond per result. This is averaged essentially across schemes. And then update protocol takes about 25 milliseconds on 2CH FP and 75 milliseconds on 2CH FPS. And finally, some key takeaways. For dynamic volume hiding, we came up with a formal game-based definition for leakage profiles. We have a first fully dynamic volume hiding scheme. The existing techniques of static volume hiding schemes were not directly applicable in most cases. We introduced 2CH based on two-just hashing. We built two further practical schemes on top of 2CH to provide forward and backward privacy, while simultaneously giving volume hiding. The difference between these two schemes is that the latter scheme has a smaller permanent client storage. Finally, we did a thorough evaluation of our schemes. The experimental evaluation in Rust showed that our constructions improve on the concrete performance of previous static and semi-dynamic constructions, which is great. And we're very close to static schemes. In fact, we got dynamicity at little to no extra cost over static schemes, which is amazing. So thank you so much.